Okay, here we go. I did it.
What is e? The two most common logarithms used are log to the base 10 and log to the base e. Why are they the most commonly used logarithms? How do we really understand them? Log to the base 10 is kind of intuitive. It's easy to talk in multiples of 10. 10, 100, 1000, and so on. Log to the base 10 gives us an easier scale to work with. Log 10 to the base 10 is 1. Log 100 to the base 10 is 2. 1000 to the base 10 is 3. And we can see that the multiples of 10 can be managed with a scale of natural numbers. But log to the base e is what I'm deeply interested in. It's called the natural log. And it's also written as ln. Yes, log to the base e is also written as ln. So log 20 to the base e can be written as ln of 20, the natural log of 20. What is this e? Some call it a magical number. Some call it an irrational constant. Some call it a Euler's number. But the harsh truth is this. Very few people actually understand what e is. To get to e, we first need to understand growth. Let's say a particular thing doubles every time period. On this timeline, this is today, and every unit is one time period. Assume you have $1 with you. At the end of the first time period, this dollar doubles and you have $2. At the end of the second period, $2 double to become $4. And at the end of the third period, we have $8. How do we look at this growth? First, we see that the numbers at the end of the time periods are powers of 2. It's in the form 2 to the power x, where x is a non-negative integer. 2 raised to 1, 2 raised to 2, 2 raised to 3, and so on. This was one way in which we looked at double growth. Another way to look at it is that there is 100% growth every time period. 1 plus 100% of 1 gives us 2. $1 was increased by 100% to get 2. In the second time period, $2 grew to $4. 2 plus 100% of 2 gives us 4, and so on. So doubling the value is the same as a 100% increase. So 2 raised to x can also be written as 1 plus 100% raised to x. It's like you're getting a 100% return on your investment. But hold on, we are making an assumption here. We are assuming that growth happens in a discontinuous fashion. We are seeing growth in steps here. What about the time in between two time periods? We are seeing no growth in between. No growth and it suddenly doubles. Again, no growth and suddenly doubles. But hey, that's not how nature functions. Everything or every kind of growth happens gradually. If your height today is 4 feet, you suddenly won't be 5 feet a year later. Your height gradually grows. When we started, we used to get around 30 views a day. And after a year, we started getting around 4,000 views a day. It doesn't mean our view count just jumped one fine day. It gradually increased. So growth in nature is never really discrete or discontinuous. Let's see how it really works. We take the example of $1 growing over 1 year at a 100% growth rate. First, we look at the annual growth. Based on what we saw, at time 0, we would have $1. And at the end of the year, we will have $2. This doesn't seem right because all the interest cannot appear on the last day. To make it slightly better, let's divide the year into 2 equal parts, 6 months and 6 months. Splitting that 100%, the growth would be 50% in the first year and 50% in the second. It would look like this. Our initial dollar earned 50% interest in the first half to give 50 cents more. Now what happens in the second half? $1.50 remains as is. The growth is 50%. So 50% of $1 will be 50 cents. And this time, the 50 cents also earned a 50% interest. That will be 25 cents. This 1.5 is the sum of our original dollar and the 50 cents we made here. So at the end of the first year, we have our original dollar, then we have the dollar that made our original dollar made, And we also have the 25 cents that these 50 cents made. A total of $2.25. This is better than doubling. If we want to understand this using a formula, it would be 1 plus 100% over 2, the whole squared. We had half the growth rate over 2 time periods. This is also referred to as semi-annual growth. Let's push ourselves further. What if we had 4 equal time periods in a year? We have divided 1 year into 4 quarters. This is how it would look. Looks messy, but it's actually...
Okay. Hold on, pause there, because you're not gonna get it if you don't pause. Okay, first of all, this is called quarterly. This is probably the most important thing that we'll do, because it's money related, and that's what we all need is money. So, the first thing I wanna tell you is that no banks are gonna give you as much money as they say in these math problems. Interest rates are terrible. They're terrible on loans, and they're terrible on bank accounts, just let you know. But, okay, so let's pretend. We'll put $1 in the bank. Okay, and 3 months in, you have your original dollar in there still, but your dollar made 25 cents. Okay, that's called interest. That's money that you get just by putting your money in the bank. So if you put your money in the bank, you get extra money. It's called interest. Are you going to get 25 cents in a month or in 3 months? Absolutely not. It's more like 1 cent. But for math purposes, we make 25 cents. The reason it's 25 cents is because that's 1/4 of a year. So it's 1/4 of your dollar. Okay, now the word compounding means that now your bank account has $1.25. Does that make sense? So compounding means literally like compounding, like squishing the interest into your account balance. So you go squish those two numbers together and you get $1.25, that's yours. And then you make 25 cents off of your original dollar and 6 cents-ish off of the 25 cents that you made. Look at all the money you get. Okay, and then compounding squishes all 3 of those together and your new account balance is $1.56. Extra. Did you guys even know that there's extra decimals in money? No. There is, you just don't see them. Okay, anyway, so this is your new account balance, and your $1.25 made that, and that made that, and that made that over the next 3 months, and then that squishes all down and you have $1.95. And then that made that, that made that, that made that, that made that, and that's gonna squish all down, and that's how much you have at the end of the year. Oh, yay, money. I have to tell you, I'm teaching you about money, but I'm terrible with it. Absolutely awful. You should see the Squishmallow collection. That is proof of my issues with money.
Very simple if you understood the concept. It's 25% growth every quarter. The formula would change to 1 plus 100% over 4, the whole raised to 4. We would approximately get $2.441 at the end of the first year.
That's awesome.
I suggest you pause the video and understand the quarterly growth diagram really well. The 100% is nothing but 1. If 2 time periods, then we have 2 here. If 4 time periods, then 4 here. So the formula for n time periods would be 1 plus 1 over n, the whole raised to n. Clearly, more the number of time periods, higher will be the returns. This will give us the dollar value at the end. I probably know what your greedy brain is thinking. Is it possible to get unlimited money? Let's make a table now. Number of time periods and the dollar value in the end. If it's just 1 time period, the dollar value is 2. If 2 time periods, then $2.25. If 4 time periods, then $2.44. If I divide the year into 12 equal time periods, my return will be higher than this. If I divide it into 365 equal time periods, it will be even higher. This tells us that $1 at the start of the year will become these many dollars at the end of 1 year if the number of time periods is 365. So if we increase this number significantly, that is if we increase the number of time periods significantly, will this number also increase significantly? Okay, here are a few more calculations. The number of time periods here is 1 million. Notice that the returns improve. Yes, they converge around a value which approximately equals 2.718. And that is your beloved E. We can't get infinite money after all. What would be a layman-friendly explanation for E then? It is the maximum possible result after continuously compounding a 100% growth over one time period. Yes, that's E. Don't forget, we had assumed a 100% growth here. And that's what E is. It's the maximum we get after a 100% continuous compounding growth over one time period. Notice what compounding does. The first result is 100% without compounding. $1 would become $2. But after continuous compounding, $1 will become $2.718 approximately. That would be a growth rate of 171.8%. That's like the maximum growth we can have. So E is approximately 2.718. It's an irrational number, which means the digits after the decimal point do not repeat and go on forever. Just one last question. What if the growth rate and the time period change? Will E still help us? Absolutely. There's no problem at all. In general, the growth after continuous compounding is given to us as e to the power r times t, where r is the rate and t is the number of time periods. So if we have a 200% growth for 5 years, then it would be defined as e to the power 2 times 5. We squared e to include 200% growth and we raised it to 5 as there are 5 time periods. It'll give us e to the power 10. E is nothing but the maximum possible result after continuously compounding a 100% growth over one time period.
So, interestingly enough, compound interest is how E is described a lot, but it's also used a lot in biology. Describes a lot about how plants grow. There's some physics applications of E. It's not just money related. So you're going to see E if you do any higher sciences. Well, what does it mean for us? It means logarithms. So there's some money applications, which we're going to start with first. These are some of my favorite problems of the year because they're just plugging in a formula and go to the calculator. Just love that so dearly. But we do have to learn how to do the logs also. I think 16. Is it 16, guys? And there's a really big chance we won't finish it. I think I mentioned this the other day. Whatever we don't finish, we'll just start on Monday. There is homework, but some people already did it, so I'm assuming it's doable. Like a bunch of people already did it. But don't worry, I'll continue whatever I don't finish. Compound interest. You learn about it in math 1 in a simple way with the y equals ab to the x. But also econ? No, I don't know. Or something else. It's very simple, which is great because we've done a lot of non-simple things lately. We're due for something simple. Me liking. And 2 of the classwork problems are just watching a video, which is, yeah. And her accent is just to die for. Okay, so what I'm gonna do is in these big spots, I'm gonna put the formulas that she was talking about in the video and put them in the middle because we're gonna do arrows to what the things mean. So this is the formula she was talking about with the 1 plus 100% over compounding time periods. Okay, so A is your new amount. So A stands for amount. That's your account balance, basically. And P stands for principal, not Miss Kleinschmidt. The principal in banking language means your initial amount. So if you see that word principal being used in a money context, that means the initial amount that was put in the bank. R is the rate, interest rate as a decimal. She was going with 100% growth. That's not going to happen in real life. Yeah, I know. Think of all the squishmallows I could buy. N is the number of times compounded per year. So she was doing like once a year, twice a year, semi-annual, 4 times a year is quarterly, 12 times a year is monthly. Daily would be 365. Those are your most common ones. And then T is time. Okay, now if the problem says compounding continuously, there's a different formula that we call PERT. PERT. And it's PE to the RT. Okay, now E is not a variable. E is a number. It's about 2.71828. So this is not a variable. It's just a number. It's a fancy number like pi. 2.718. Okay, and if you go on your calculator, there's an E button. It's over in the log section because that's where it belongs. Okay, so over here, we've been using this as our log base 10 button. Right below that, you might have seen this guy. This is called log natural, or natural log. They call it log natural because the calculator has a catalog in it. They wanted to keep the logs together, so they started it with L. And then e to the x is right above that, printed on the calculator. So if you hit second natural log, you'll get e to the, and then just put a 1 in there, e to the 1, 2.718, blah, blah. It goes on forever like pi, but calculator will give you the first few. Okay. We'll see if we can just get through this part and then do 179, which is actually a resource page when we come back on Monday. Okay, so I'm just gonna write these out. I know you guys are still writing. This is very simple though. Okay, so A equals, I am looking at the formula above it. Quarterly is time periods. The principal in this case is $10,000. That's the initial amount put in. 1 plus, the rate is 3%, so write it as a decimal. And quarterly means 4 times per year. And then N is 4 up here also, and then it says for 10 years. And then you just type that in the calculator. Mm-hmm. Mm-hmm. So very important with these problems, round to the nearest penny. So you want 2 decimal places for all of these so that you don't look uneducated. $13,483.49. And I didn't do anything fancy with typing it in. I put this as divided by, I didn't try to make that a fraction or anything. Okay, now the continuously is PERT. So principal, no parenthesis. I don't know why I put a parenthesis. Okay, and then E. E again is a number. It's not a variable. And then rate is 0.03 and time is 10. So PE to the RT. So you go 10,000. Second natural log, 0.03 times 10 up in the exponent. So just a little bit more money for continuously. Continuously should always be the most. So if you get more for something else, you did it wrong somewhere, but that's really it for that. I love it. It's amazing. We'll do 179 on Monday, so we'll start with that.